Hi, today we'll go over palindrome linked list problem. The problem statement is, given the head of a singly linked list, return true if it is a palindrome. I will go over two solutions. The first solution will be based on a stack, and the second solution will be the optimal linear time, constant space, complexity solution. I will start out by defining what a palindrome is, and then I will give some intuition on how to solve the problem. A palindrome is the word that reads the same forward as it does backwards. So for example, Katek, when read backwards, is still Katek. However, forest, when you read it backwards, you get serif. It does not read the same way forward as it does backwards. Therefore, forest is not a palindrome while Katek is a palindrome. Another way to view this problem is when we take our given word and reverse it. If it's still equal to the original word, then it's a palindrome. So one of the approaches to solving this problem would be to take our given linked list, make a copy, and then reverse the copy of it. And then compare the original linked list with the reverse copy of it. And if the two happen to be equal, then our linked list is a palindrome. However, in case of Katek, we don't really need to compare the entire word. We just need to compare the first two elements, and then we'll know if it's a palindrome. And similarly for the forest, just comparing the first three elements would tell us whether or not the word is a palindrome. That is because to know if something is a palindrome, we just need to compare the first letter with the last one, then the next one with the next to the last one. And if the word has an odd number of letters, as in Katek, the middle node would get compared to itself, so we technically don't even need to compare it to anything. So solving this problem in a more efficient way is a matter of taking one of the halves of the word, reversing it, and comparing it to the other half. Now I will illustrate the stack solution of this problem. So when solving this problem, we first need to find where the middle of the linked list is. It is typically done using two pointers. One pointer is fast and the other one is slow. So the slow one moves one node at a time, while the fast one skips a node, so it moves two nodes at a time. So when the second pointer reaches the end of the linked list, we know that the slow pointer points to the node in the middle, which in this case is 2. When we have odd number of elements, the slow pointer will end up in the middle when the fast pointer will reach the last node in the linked list. So in this way, we can find the middle of a linked list. As the slow pointer traverses the linked list, we could record the values it encounters in a stack. So we'll record the value of the first node, then when we reach the second one, we'll record the value of the second node. However, the moment the slow pointer reaches the middle of the stack, we will continue traversing the linked list, except we will start popping values off of the stack. So in this case, we will pop 1 off of the stack and compare it to the value of the node our slow pointer is pointing to. And then as we go along, we can pop off more elements and compare them. If they all are equal to each other and we reach the very end, then great, we have a palindrome, and if not, we return false. In case when we have an odd number of elements, we actually would want to skip the middle before beginning to pop elements from our stack and comparing them. So using the stack approach, we basically take the first half of our linked list, reverse it, and then compare it to the second half. Finally, getting into code, I will define my slow pointer, my fast pointer, and my stack. And then I will begin traversing the linked list. So here, while fast pointer is not null, at each iteration we would want to move the slow pointer ahead by 1 node and the fast pointer ahead by 2 nodes. And we would want to push the value of the node the slope pointer is at onto our stack. This works for the case with even number of elements, because when we have an even number of elements, when the fast pointer becomes null, our slow pointer is exactly in the middle. However, when we're dealing with an odd number of elements, the slow pointer is in the middle when the fast pointer reaches the very last node in our linked list. So I will need a separate check for this condition. So I will check if my fast pointer is at the very last node of our linked list. If fast.next is null, I know I have a linked list with odd number of elements and the slow pointer is exactly in the middle. And when I'm dealing with the case where my linked list has an odd number of elements, I would want to skip the middle node and not do anything with it. And now that I have my stack populated by elements from the first half of the linked list and my slow pointer points to the start of the second half of the linked list, I can just traverse through the second half of my linked list. I would still be incrementing my slow pointer by 1. And as I'm doing that, I will be popping elements off of my stack and comparing them to the value of my slope pointer. If the two values are not equal to each other, then I'm going to return false. If I make it to the end, then I indeed have a palindrome, so I'm going to return true. And then I will submit this code. It works and it is accepted. This is a linear time, linear space complexity solution. Now moving on to the optimal solution that uses constant space, I will first find my midpoint. Then, starting at my midpoint, I will reverse the second half of my linked list, and then I will compare the first half of my linked list to the reversed half and return the value. So here I sketched out my solution, and now I will code out my subroutines. Just to be consistent on style, I will change it to arrow notation. So here I'll have const find midpoint is equal to head, and we know that to find midpoint we would need a slow pointer and a fast pointer, and then we would traverse our linked list. At each step we will increment the slow pointer by 1 and the fast pointer by 2 nodes. And at the end, we will return our slow pointer, which will be in the middle. Now I will write a function to reverse a linked list. I will need to keep track of my previous element and my current one, and then I will traverse the list, reversing my elements. For the current one, I would need to set the next key to be equal to the previous node. Then I would need to update my previous node to be equal to current for the next iteration, and I need to update my current node to be equal to the next one. Oh yeah, and preven current need to be lets instead of consts. And so I would want to record what the next element is before I change it. And at the very end, I will return my previous value. Just to give a visual of what is happening, we're taking the next link and we are reversing it at each step. So then we'll remove the link from 2 to 3 and change it to be from 2 to 1. To go into more details, here, for example, when we arrive at 3, our current value will be equal to 3. Our previous value would be equal to 2. Then we set next to be equal to cur.next. And then we change cur.next to point to the previous one. And then we update current to be equal to next and prev to be equal to current. Until finally our current pointer points to null And in that case, our previous pointer points to the node before last one. When we return previous one, we are actually returning a reference to the start of our reversed linked list. And now I will implement the compare function. The function will take both lists as its argument, and then it will traverse through them while neither one of them is null. So at each point, we want to increment both lists by one node. At each step, I want to compare the values of list 1 to list 2. If they're not equal to each other, I will return false. Otherwise, I will return true. In the end, my palindrome function finds the midpoint, reverses the second half of the list starting at the midpoint, and then compares the reversed second half to the first half. Now submitting it, it is accepted. So this is linear time complexity, constant space complexity, optimal solution. There are numerous ways of implementing the details. However, the idea is the same. I found this problem a little more challenging to talk about since linked lists are fairly abstract, but I hope this explanation was clear and helped you understand this problem better. Thanks for watching, and I hope you do well on your interviews.